Okay, today's topic is talking about logistic growth, and you guys were introduced to logistic growth back in pre-calc, and it is always included with exponential and logarithmic because if you remember logistic growth is something that will start growing exponentially, but it's a more real-world model of exponential growth, and that is like maybe the population of a town is going to grow exponentially, but you can't fit infinite people in a town or in a country. And so at some point, whatever is being described by that logistic growth will hit a point where it will level off when it gets to its maximum value. And that's a real world exponential situation, is that things don't grow exponentially forever. They can grow exponentially for a while, and then they end up leveling off. So, looking at some things around logistic growth. This one would be a model. If you guys remember what your logistic growth models look like, it was always some number over 1 plus e raised to some number, and that's where that exponential piece comes into play. This logistic model that they gave us is describing the spread of flu. And if you think about that spreading through a school, once somebody gets it, then a whole bunch of people all of a sudden are gone in your class the next day, right? So that's where the fast part of the exponential growth happens. And at some point, either everyone's gotten it or everyone who's going to get it kind of levels off there. And that's where we see the leveling off happens. There's only so many people that can get the flu, right? So it would level off. This one says P of t is the total number of students infected after t days. So again, kind of reading that gives us our labels as we look at labeling our answers in there. The first question says, estimate the initial number of students infected with the flu. When it says estimate the initial would be time equals what? 0, right? Initial means the start. So when they're asking you to estimate the initial, they are asking you to evaluate your function for time equals 0. So this is going to be kind of an ugly number. Grab your calculators. Let's evaluate that function, P of t, for 0. Okay, now this does come out to an ugly number. Go ahead and give me 3 decimals after it. I know it's people, but. And P of t is the total number of students. So that would be 4.73 students. Okay, so almost 5. Could have a discussion on whether you just say 4 because the next person hasn't fully been infected, or whether we say it's approximately 5 students. But guys, it's AP. You round to 3 decimal places. Okay, so it doesn't matter that we're talking people here. You can just say 4.743 students. Okay. All right, the next question, how fast is the flu spreading? When we are talking fast, how fast, that is speed, and speed is velocity or the rate of change, right? So they're asking you to look at the derivative of the function. All getting that from that question when they're asking about the rate, about the how fast, which is speed. Is it spreading after 3 days? They're asking us to do our derivative and evaluate at 3 days. Evaluate it for time equals 3. Now, on a problem like this, typically we would get a calculator because that's a really ugly problem. I can do this one without a calculator and actually do the derivative. I do want to remind you, you guys do have a derivative function on your calculator, that numeric derivative, Math 8, that we could type this into. I'm going to go ahead and do the derivative up here just to continue to practice taking derivatives when we don't have a calculator. So if I were to look at doing the derivative of this, first of all, I would like to manipulate the function because it's easier to do. If the numerator of this fraction is just a constant, I can just slide this up to the top and make it raised to the -1, can't I? So this is really 100, let me slide that over, times 1 plus e to the 3 minus t raised to the -1. That's the same function. And rewriting it that way just allows me to then do just chain rule here, because 100 is just a number. I don't have to do like product rule or anything. So doing chain rule to find my derivative of this, -1 times 100 would be -100. Subtract 1 raised to the -2. Don't change the inside. This is a good time for us to remember how to take the derivative. So now chain rule, take the derivative of the inside. Derivative of 1 is 0. Derivative of e to the 3 minus t. To do e raised to the something, we do the original, e to the 3 minus t, times the derivative of the exponent, and the derivative of 3 minus t, derivative of 3 is 0, derivative of minus t would be -1. Cleaning all of that up, -1 times -100 is 100. That's in my numerator. This would go back to my denominator because of the negative. And I'm supposed to evaluate that at time equals 3. So again, grab my calculator, type in 3 to that. What are we getting? What is it? I feel like it's not 50. $25. I think it's 25. I think when we type 3 into that, we get 25. Now, let's talk label. That is the derivative of our function. So think about what the label is. The label is always going to be the function's label over the time, right? So our function is in students. Our time is in days, which means the rate of change would be in students per day, right? 25 students per day is what rate we are changing on day 3. Any questions on that one? Okay. I do want to look at the calculator a little bit, and that's going to help us with this last one. When will the flu spread at its maximum rate, and what is that rate? So again, it's asking us for the maximum of the velocity, the maximum of the derivative there. But let's go ahead and grab our calculators, and I want to look at just anything to do with logistic growth on our calculators. How do I find a window that can appropriately show me that picture? So let's go ahead and type our original function into y1. Okay. And then it comes down to setting my window, right? So there's, first of all, just some things we have to understand about the whole logistic growth thing and what's going on. Our variable is time, is your x-axis, and time would start at 0 days, right? That's initial. So as I go to set my window, I would want my x minimum to be 0 because we're not going to look at any graph less than time equals 0. The maximum of it, in logistic growth, you find it does not take long to hit that maximum. So that's going to be kind of a guess and check, but that picture that I drew at the beginning, when you pick this x max, you want to be able to make sure that you can see all of that. If you are not seeing where it's increasing quickly and then leveling off, you probably haven't gone far enough. I would try 10, 15, 20, somewhere in there. Think about how many days it would take to infect people in a school, how quickly that's spreading. Y stands for our students, right? And we would have the least amount of students we would have is 0. The maximum, now this goes back to what you guys learned about logistic growth last year. Do you remember where to look to find a maximum on your logistic growth model? Numerator. It's your numerator. Our numerator is 100. I do like to be able to see the whole thing, so I give myself a little breathing room. If the maximum is going to be 100, I would maybe go up to 110, 120, something a little above that so that I am not going to run right into the top of my graph there. I changed my scale so I don't have 120 little tick marks right there. And then I see a picture, and that's exactly the shape we were looking for, right? So it starts out increasing very quickly, exponentially, and then it starts leveling off as it gets up to its maximum value. That's your logistic function. The question we were working on down here asks us to talk about when will it spread when will the flu spread at its maximum rate. So we want to look at our rate, which would be our velocity. So then I'm going to graph my velocity function. You don't have to do both of them on the same graph, but I'm just going to leave that one on there. Look at our velocity graph here. Let's see, what was it? 100 E. Is that right? Top of it. Okay. And as I look at that rate, it should make sense. It is all above here. It is all above my x-axis because we will always have a positive slope on this until we get up to where it's flatlining, and that's where it gets to 0 because the rate stops changing and becomes constant, which means our rate of change becomes 0, no change, right? So it's asking us when will it be at its maximum, and that's the maximum of that red line. If we have a calculator for a problem like this, that is where I can just go to my calculator and find the maximum. Make sure you're on the right graph there, since I had both graphed. Okay, move a little bit left of the maximum. Move a little bit right of the maximum, and it will tell me that the maximum rate is 25 at time equals 3. So that answers both parts of this question. When will it spread the fastest? That's at 3 days. What is the maximum rate? And the maximum rate was 25 students per day, which confirms what we got as an answer in part 2 of 25 students per day at time equals 3. Okay. Now the question is, will we always get a calculator if we're asked to find the maximum of our rate? We won't. On a question like this, you would have to, because the only other way to find this would be to look at the zeros of the acceleration. We're going to spend a ton of time doing that eventually. To find the zeros of the derivative of that would be near impossible without a calculator. So, no. Something like this, questions like this, eventually yes, but the functions will not be as complex. Okay? Questions for me? All right. Your assignment tonight, page 184.